Welcome back to The Explainer. Today, we're tearing into a brilliantly clever piece of modern computing, operating system memory management. Specifically, we're looking at how it scales up to handle absolutely massive demands using a concept called multi-level paging. It is so fascinating how our computers organize their thoughts behind the scenes, and we're going to uncover exactly how they pull it off. Okay, let's dive into this. Have you ever wondered how your OS manages just massive amounts of memory without completely bogging down and crashing? I mean, every single program you run needs space, right? And keeping track of exactly where all that data lives requires an incredibly complex map. But what happens when the map itself becomes way too big to hold? That right there is the massive scale of the problem we're solving today. So here is our roadmap, which honestly is kind of acting like an outer page table itself, pointing us to the inner sections of today's explainer. We'll hit the single-level memory problem, enter multi-level paging, explain the hierarchical structure, look at the advantages of saving main memory, and finally, the disadvantages of slower address translation. Section 1. The single-level memory problem, why monolithic tables fail. So, in a traditional single-level paging system, the setup is straightforward but honestly highly restrictive. Every single process running gets one page table to map its virtual memory to physical hardware frames. But here is the critical flaw. In modern systems with massive 32-bit or 64-bit address spaces, this single table becomes huge, like entirely too large to fit into a single contiguous memory frame. Imagine having a directory so massive that you literally can't even fit the directory itself into your filing cabinet. And this brilliantly illustrates the core conflict. That single-level approach is monolithic, just one massive table per process. And it utterly fails because it demands too much unbroken contiguous space. It's just too big for one standard frame. But multi-level paging steps in as the hero of our story here because it divides that massive data into smaller, manageable chunks that fit perfectly into standard memory frames. Section 2. Enter multi-level paging, the clever hierarchical workaround. So the crucial point is that multi-level paging takes that problematic, massive page table and breaks it down into a hierarchical tree structure. Why? Well, because it strictly prevents the system from having to load the whole massive table into RAM all at once. By breaking it up, you significantly shrink the memory footprint. Section 3. The hierarchical structure explained. Anatomy of a logical address. Instead of a single massive index, a virtual address gets split into segments. Step 1 is the outer page table. This first part points you to the base address of a secondary table. Then, step 2 uses inner page tables, acting as indices to jump down the tree toward the final physical frame. And finally, step 3 is the offset, which points to the exact byte you need within that physical frame. Let's move to a concrete breakdown and see how this builds out. In a standard two-level paging system, your virtual address is mathematically split into three distinct parts. You've got P1, which is your outer page table index, then P2, your inner page table index, and finally D, the offset within the physical frame itself. It's basically a simple three-step treasure map that leads the CPU exactly where it means to go. Section 4. Advantages. Saving main memory. The power of sparse allocation. Sparse memory allocation is an absolute game changer. It means that only the page tables actually in use right now need to reside in main memory. If a process isn't using huge portions of its virtual address space, well, those tables are simply never created or allocated in the first place. It acts as a massive, massive RAM saver. Now, what's really interesting about this flexibility is how effortlessly it accommodates vast logical address spaces. It remains highly efficient when a program's total memory usage is relatively low. And most importantly, it completely avoids that fatal flaw we talked about earlier of having to load massive, monolithic tables into RAM all at once. Section 5. Disadvantages. Slower address translation. The cost of complexity. Now, in computer science, there is always a trade-off, right? Breaking things into a hierarchical tree structure means we now have to actually navigate that entire tree. Because the CPU must physically traverse multiple levels of these tables, our hardware and software structures become inherently more complex. You are now requiring multiple memory accesses just to resolve one single address. Let's make this drawback super concrete. Think about the number 4. If you've engineered a multi-level paging setup with 4 levels, well, translating a single address requires 4 separate memory accesses. Every single level you add to save space directly bogs down the speed of your translation. So, let's bring this all together and summarize the arc of our explainer. On the plus side, we've solved the space crisis. We get massive memory savings, we facilitate highly efficient, sparse allocation, and we gain incredible flexibility for large address spaces. But, balancing the scales on the flip side, we definitely pay a tax in speed and complexity. We suffer from slower address translations, we require multiple memory accesses per lookup, and we demand inherently more complex hardware and software just to keep the whole tree functioning. Which leaves us with a final, provocative question for today. In computer science, is the memory we save ultimately worth the processing speed we sacrifice? It's the eternal balancing act of system design, and honestly, multi-level paging is one of the most brilliant compromises we've ever engineered. Thank you so much for joining me to explore this topic today. Keep learning, keep questioning, and I will catch you on the next explainer.